the solar system, ASMR, a relaxing journey through the planets. Welcome to the cosmos. Hello, and welcome back to your midnight library. Take a slow, deep breath with me, and another, letting all the tension of your day just drift away, like stardust scattering gently into the peaceful darkness. Tonight, we're going on a journey together, a journey through the solar system, our cosmic neighborhood, our home among the stars. And I want you to know you don't need to do anything except relax and listen and let yourself float. Float with me through the most beautiful, serene, and wondrous places in all of space. So settle in now, adjust your pillow, pull your blankets up just so, and close your eyes if you haven't already. Imagine yourself lying on your back on a warm summer night, looking up at the sky. The air is perfectly still, gentle, comfortable against your skin. Above you, thousands upon thousands of stars glitter like diamonds scattered across black velvet, each one a distant sun, each one telling a story that began billions of years ago. Can you see them? The stars twinkling softly, some bright, some dim, painting patterns across the darkness. The Milky Way, our galaxy, stretches overhead like a river of light, a celestial path leading us home. And as you gaze upward, you feel yourself becoming lighter, lighter and lighter, as if the earth beneath you is gently releasing its hold. You're floating now, rising slowly, peacefully, up through the atmosphere, up past the clouds, higher and higher into the velvety darkness of space itself. Don't be afraid. You're safe here. Space is quiet, so wonderfully quiet, and you're surrounded by gentle starlight, by the soft glow of distant worlds. You can breathe easily, comfortably, as if you're still in your bed, which of course you are. This is just a journey of the mind, a peaceful exploration of scientific wonders that will soothe you, calm you, and carry you gently into the deepest, most restful sleep. Now, before we begin our tour through the planets, let me tell you a story that began 4.6 billion years ago. That's 4,600,000,000 years. Can you imagine? So long ago that our minds can barely grasp it. Back then, where our solar system now exists, there was a vast cloud, a molecular cloud. Astronomers call it a nebula, stretching for trillions of miles through space. It was made of gas, mostly hydrogen, the simplest element, with some helium and just the faintest trace of heavier elements, carbon, oxygen, iron, elements that had been forged in the hearts of ancient stars that had lived and died long before our sun was born. This cloud was dark, cold, peaceful, drifting slowly through the galaxy for millions of years, perhaps hundreds of millions. It existed like this, undisturbed, serene. But then something happened. Perhaps a nearby star exploded in a supernova, sending a shockwave rippling through space, or perhaps two giant clouds gently collided. Whatever the cause, a disturbance, a gentle push, set something wonderful in motion. The cloud began to collapse. Parts of it, drawn together by gravity, began to pull inward, spiraling slowly, creating eddies and currents in the gas. Imagine it, this vast cosmic ballet, particles of dust and gas millions of miles apart beginning to dance together, to spiral, to concentrate. At the center, where most of the mass was gathering, the cloud grew denser and hotter. The pressure increased, atoms pressing together, spinning faster and faster, generating warmth, then heat, then searing temperatures. This would become our Sun. Around this forming star, in a disk of remaining gas and dust, smaller clumps were forming. These clumps collided, stuck together, grew larger. Pebbles became boulders. Boulders became mountains. Mountains became planetesimals, and planetesimals, through countless gentle collisions over millions of years, became the planets we're about to visit. Some planets formed close to the Sun where it was hot, where only rock and metal could survive. These became the terrestrial planets: Mercury, Venus, Earth, and Mars. Small, dense, solid worlds. Farther out, where it was cold enough for ice to form, the giant planets grew: Jupiter, Saturn, Uranus, Neptune. They captured vast atmospheres of hydrogen and helium, becoming enormous, beautiful, swirling worlds of gas and cloud. And beyond even these, in the frozen outer reaches, countless small icy bodies remain, remnants from the solar system's birth, like cosmic time capsules preserving the ancient past. All of this, everything we're about to explore, came from that one collapsing cloud. We are children of the nebula, you and I, made of the same elements that formed the planets, the same hydrogen that lights the Sun, the same carbon that forms the foundation of life. We are, quite literally, made of stardust. So now let's begin our journey. We'll start at the center with the star that makes everything possible, and then drift outward, slowly, peacefully, visiting each world in turn. Take your time. There's no rush. We have all the time in the universe. Let's go meet the Sun. The Sun, our star. Here we are, floating in space, and before us, the Sun. But we're far enough away to be safe, far enough to admire it without being overwhelmed. From here, about 93 million miles away, the distance we call an astronomical unit, the Sun appears as a brilliant golden sphere, perfect, luminous, powerful yet gentle in its distant glory. It's so bright it illuminates everything, but its light doesn't hurt your eyes here in our imagination. Instead, it warms you, soothes you, fills you with peace. This is the light that touches your face every morning, the light that makes life possible, the light that has shone, largely unchanged, for 4.5 billion years. Let me tell you about this magnificent star. The Sun, our Sun, contains 99.8% of all the mass in the entire solar system. Think about that. Jupiter, Saturn, all the planets, all the moons, all the asteroids and comets combined make up less than 0.2%. The Sun is everything. It is the gravitational anchor, the center around which we all orbit, the source of nearly all energy in our corner of space. If you could measure it, the Sun is about 865,000 miles across. That's roughly 109 Earths lined up side by side. You could fit 1.3 million Earths inside the Sun's volume. It's so vast, yet from Earth it appears as a small disk in our sky because of the immense distance. Now let's drift closer in our imagination and see what's happening inside this stellar furnace. At the Sun's core, buried deep beneath layers of stellar matter, something extraordinary occurs. The temperature there is about 27 million degrees Fahrenheit. 27 million. The pressure is crushing, unimaginable, 250 billion times the pressure at Earth's surface. In these extreme conditions, hydrogen atoms are forced together. 4 hydrogen nuclei, the simplest atoms in the universe, fuse together to form one helium nucleus. This is nuclear fusion, and when it happens, a tiny amount of mass is converted directly into energy, into light, into the warmth that makes planets habitable. This process, fusion, releases more energy than any chemical reaction ever could. Every second, the sun converts about 600 million tons of hydrogen into helium. Every single second. And it's been doing this for billions of years and will continue for billions more. The energy created in the core doesn't escape immediately. It begins a long journey outward through different layers, each with its own character. First, the energy passes through the radiative zone. This region extends from the core about 70% of the way to the surface. Here, photons of light, tiny packets of energy, bounce randomly from atom to atom like a pinball in slow motion. A single photon might take 100,000 years just to travel through this zone. Imagine, light that reaches your eyes today began its journey in the sun's core long before human civilization existed. Beyond the radiative zone lies the convective zone. Here, the plasma becomes less dense and energy transfers differently. Great currents of hot plasma rise toward the surface, cool, and sink back down. Like water boiling in a pot, but on an enormous scale. These convection cells, each one larger than Earth, create a constantly churning, dynamic layer. You can actually see the effects of these cells on the sun's surface if you observe it through a proper solar telescope. The surface appears granulated, like the skin of an orange, each granule a convection cell bringing heat from below. Finally, we reach the photosphere, the visible surface of the sun, the part we see from Earth. This is where photons finally escape into space after their long journey from the core. The photosphere is about 300 miles thick and has a temperature of around 10,000 degrees Fahrenheit. It's here that we see features like sunspots. Sunspots are darker patches on the sun's surface, appearing dark only because they're cooler than their surroundings, though still incredibly hot at about 6,500 degrees. They're caused by intense magnetic activity that inhibits convection, preventing some heat from reaching the surface. Sunspots can be enormous, some larger than Earth itself, and they wax and wane in an 11-year cycle as the sun's magnetic field flips and reorganizes itself. Above the photosphere lies the chromosphere, a thin layer of the sun's atmosphere. During a total solar eclipse, when the moon blocks the bright photosphere, you can see the chromosphere as a thin reddish ring around the sun's edge. This color comes from hydrogen atoms emitting red light. The chromosphere is hotter than the photosphere beneath it, reaching temperatures of about 35,000 degrees. And scientists are still working to fully understand why the atmosphere gets hotter as you move away from the surface. Beyond the chromosphere stretches the corona, the sun's outermost atmosphere. The corona extends millions of miles into space, forming a glowing halo visible during solar eclipses. It's extraordinarily hot, reaching temperatures of over 2 million degrees Fahrenheit, though the plasma is so thin you wouldn't feel its heat if you could somehow survive there. The corona is shaped by the sun's magnetic field, creating beautiful streamers and loops of glowing gas. From the corona, a stream of charged particles flows constantly outward. This is the solar wind, a gentle yet persistent breeze of protons and electrons that fills the entire solar system. The solar wind travels at about 1 million miles per hour, carrying the sun's magnetic field with it, creating what we call the heliosphere, a vast bubble that encompasses all the planets and extends far beyond Pluto. The solar wind shapes our solar system in subtle ways. It sculpts comet tails, always pushing them to point away from the sun regardless of the comet's direction of travel. It interacts with planetary magnetic fields, creating auroras on Earth, Jupiter, Saturn, and other worlds. And far, Far out at the edge of the solar system, the solar wind finally meets the interstellar medium, the thin gas between stars, creating a boundary called the heliopause where our sun's influence ends. Sometimes the sun becomes more active, releasing sudden bursts of energy called solar flares or ejecting huge clouds of plasma in coronal mass ejections. These events can be powerful, but from Earth they're distant whispers, creating beautiful auroras and occasionally affecting satellites and power grids, reminders that our star, while stable and life-giving, is also dynamic and alive with energy. The sun has been shining for about 4.6 billion years. In that time, it has grown slightly brighter, about 30% brighter than when it first formed, as helium ash builds up in its core and changes the fusion process subtly. It will continue shining steadily for about another 5 billion years before its hydrogen fuel begins to run low. When that distant time comes, the sun will swell into a red giant, growing so large it may engulf Mercury, Venus, and possibly Earth. But that's so far in the future, it's beyond our comprehension. And for now, for all of human history and far into our future, the sun will remain stable, warm, and nurturing, the golden heart of our solar system, the source of light and life for our world. Take a moment to appreciate this magnificent star, this ordinary yellow dwarf that is nevertheless everything to us. Feel its warmth even from 93 million miles away. This is the same warmth that dried the first oceans that formed on primordial Earth, the same light that powered the first photosynthesis in ancient microbes, the same energy that sustained the dinosaurs and now sustains us. We owe everything to the sun. Now, let's begin our journey outward through the solar system. Our first stop is the closest planet to the sun, a small, swift world baked by solar radiation yet harboring surprising secrets. Mercury, the swift messenger. We're drifting away from the sun now, traveling inward toward its nearest companion, and there, growing larger in our view, is Mercury. It's a small world, only slightly larger than Earth's moon, just over 3,000 miles across. From this distance it looks grey and heavily cratered, ancient and peaceful. A world that has remained largely unchanged for billions of years. Mercury is named after the swift Roman messenger god, and it's easy to see why. This little planet races around the sun at nearly 30 miles per second, completing an orbit in just 88 Earth days. It's the fastest moving planet in our solar system, forever running its quick circuit around our star. But despite its swift orbit, Mercury rotates very slowly on its axis. In fact, it takes 59 Earth days for Mercury to complete one rotation. This creates a strange relationship between its day and its year. Mercury rotates exactly 3 times for every 2 orbits around the Sun, a phenomenon called spin-orbit resonance. This means that if you stood on Mercury's surface, you would experience a day, from one sunrise to the next, that lasts 176 Earth days. 2 Mercurian years pass in a single Mercurian day. Let's drift closer and observe this enigmatic world. The first thing you notice is how close Mercury is to the Sun. At its closest approach, it's only 29 million miles away. The Sun in Mercury's sky appears almost 3 times larger than it does from Earth, dominating the black heavens with fierce brilliance. This proximity creates extreme temperature variations, perhaps the most extreme of any planet in the solar system. During the long Mercurian day, the side facing the Sun bakes in temperatures reaching about 800 degrees Fahrenheit, hot enough to melt lead and zinc. The rocks themselves can almost glow with stored heat. But Mercury has virtually no atmosphere to retain this heat or distribute it around the planet. It has what's called an exosphere, an extremely thin collection of atoms blown off the surface by the solar wind or released by radioactive decay. But it's so tenuous it might as well be a vacuum. With no atmosphere to trap heat, nighttime on Mercury is bitterly cold. As the planet slowly rotates and the sun sets, temperatures plummet dramatically. The long night sees temperatures drop to about -290 degrees Fahrenheit. That's a temperature swing of over 1,000 degrees, the most extreme in the solar system. One side of the planet bakes while the other freezes, separated by a terminator line where eternal twilight reigns and temperatures are almost comfortable by planetary standards. Now observe Mercury's surface as we glide above it. The landscape is heavily cratered, a testament to billions of years of impacts from asteroids and comets, without an atmosphere to burn up incoming objects or weather to erode the scars. Every impact remains visible, a geological record stretching back to the solar system's violent youth. The craters range in size from tiny pits to enormous basins. Some have bright rays of ejected material stretching outward, while others are smooth and ancient, their features softened by countless smaller impacts over time. One feature stands out dramatically: the Ceres Basin, one of the largest impact structures in the solar system, stretches about 960 miles across. This enormous crater was formed when an asteroid perhaps 60 miles wide struck Mercury billions of years ago with such force that it created shock waves that traveled through the entire planet. On the exact opposite side of Mercury from Ceres, you can see strange jumbled terrain where these shock waves converged, fracturing and disrupting the surface. Between the craters, you notice smooth plains of ancient lava flows. Mercury experienced volcanism in its past, with molten rock flooding across its surface and filling in some of the older impact basins. These volcanic plains are now cold and solid, frozen in time. Looking more closely, you see strange features called Lobati scarps, long cliffs that snake across the surface for hundreds of miles. These scarps are wrinkles in Mercury's crust, formed as the planet cooled and contracted over billions of years. As Mercury's interior solidified and shrank, its surface had to adjust, buckling and creating these cliffs, some up to 2 miles high. This shrinking is ongoing. Mercury has contracted by about 7 miles in diameter since it formed, and it's still slowly shrinking today as its core continues to cool. It's like a dried fruit, wrinkling as it loses volume. Except this fruit is an entire world. Mercury's core is unusually large for such a small planet. Its iron-nickel core makes up about 75% of the planet's diameter, a much larger proportion than any other terrestrial planet. Scientists believe that Mercury may have formed with a thicker rocky mantle that was stripped away by a giant impact early in the solar system's history, or perhaps the intense heat from the nearby sun vaporized much of the lighter rock, leaving behind this dense, metal-rich world. This large core gives Mercury a magnetic field, albeit a weak one, only about 1% as strong as Earth's. But it's surprising that Mercury has any magnetic field at all, for a planet so small. Most scientists expected the core to have solidified completely, which would have stopped the dynamo effect that generates magnetic fields. The fact that Mercury has a magnetic field suggests that at least part of its core remains molten, perhaps with a solid inner core and a liquid outer layer, much like Earth's core structure. The magnetic field creates a miniature magnetosphere around Mercury, a bubble of magnetic influence that deflects some of the solar wind. The solar wind is intense this close to the sun, and Mercury's magnetosphere constantly wrestles with it, creating a dynamic, ever-changing boundary. Now, here's one of Mercury's most surprising secrets. Despite the baking temperatures on the sunlit side, there's water ice on Mercury. Scientists discovered this when radar observations revealed highly reflective patches at Mercury's poles. These patches match perfectly with deep craters whose floors lie in permanent shadow. In these shadowed craters near the poles, sunlight never reaches. Temperatures remain constantly below -300 degrees Fahrenheit. Here, water ice delivered by comets over billions of years has accumulated and remained frozen, protected from the sun's fierce heat by nothing more than shadow. Some craters may contain ice several feet thick, and this ice may even be covered by a layer of dark organic compounds, further insulating it from any stray sunlight. It's remarkable to think of ice existing on one of the hottest worlds in the solar system, a reminder that the universe is full of unexpected contrasts and hidden wonders. Mercury has been visited by only 2 spacecraft. Mariner 10 flew by 3 times in the 1970s, mapping about 45% of the surface. Then, decades later, the Messenger spacecraft orbited Mercury from 2011 to 2015, mapping the entire planet in detail and revealing its magnetic field, its ice deposits, and its complex geology. What Messenger showed us was a world more active and interesting than anyone expected. Mercury isn't just an inert ball of rock. It has a complex history of volcanism, tectonics, and interaction with the solar wind. It's a world that has much to teach us about planetary formation and evolution. As we prepare to leave Mercury and continue our journey, take one last look at this swift, battered world, so close to the sun, yet harboring ice, so heavily cratered, yet geologically dynamic, so small, yet magnetically active. Mercury is a world of extremes and contradictions, a testament to the complex physics and chemistry that shape the planets. Our next destination is a world that from Earth appears as a brilliant evening or morning star, shining with a beauty that has captivated humanity since we first looked up at the heavens. A world that is Earth's twin in size but utterly alien in character. Venus. The veiled world. We're traveling outward now, away from Mercury and the intense heat near the sun, toward the second planet, and there she is. Venus, growing in our view, even from space. Venus is beautiful. The entire planet is wrapped in thick clouds that completely hide the surface. These clouds are brilliant white, reflecting most of the sunlight that hits them, making Venus the brightest natural object in Earth's night sky after the moon. Ancient peoples called her the morning star or evening star, though of course she's not a star at all, but a planet, our nearest neighbor in space. Venus is nearly identical to Earth in size and mass. She's about 7,500 miles in diameter, only slightly smaller than Earth, and her gravity is about 90% of Earth's. Because of these similarities, early astronomers imagined Venus might be Earth's sister world, perhaps covered in warm oceans and lush tropical forests beneath those perpetual clouds. But as we've learned more, we've discovered that Venus is anything but Earth-like. She is a hellish world, the hottest planet in the solar system, with an atmosphere so thick and crushing it would feel like being deep underwater, and clouds made not of water, but of sulfuric acid. Let's drift closer and learn about this veiled mystery. Venus orbits the Sun at about 67 million miles, closer than Earth, but farther than Mercury. She takes about 225 Earth days to complete one orbit. But here's where Venus becomes truly strange. Her rotation is extraordinarily slow and, even more remarkably, backward. Venus rotates retrograde, meaning she spins in the opposite direction from most other planets. If you could see through her clouds to watch the sun rise, you would see it rise in the west and set in the east, and this rotation is glacially slow. Venus takes 243 Earth days to complete just one rotation. This means a Venus day is actually longer than a Venus year. The planet completes an orbit around the Sun before completing a single rotation on its axis. Why does Venus rotate backward and so slowly? Scientists aren't entirely sure. It may have been caused by a massive impact in Venus's early history that knocked the planet over and reversed its spin, or perhaps tidal forces from the thick atmosphere gradually slowed and reversed the rotation over billions of years. It remains one of Venus's many mysteries. As we approach, we can see the cloud layers more clearly. The clouds form at about 30 to 40 miles above the surface and extend upward for another 20 miles or so. They move rapidly, circling the entire planet in just 4 Earth days, driven by winds that race through the upper atmosphere at over 200 miles per hour. This phenomenon is called superrotation, with the atmosphere moving much faster than the planet itself rotates. The clouds themselves are composed primarily of sulfuric acid droplets. Sulfur dioxide released from volcanic activity reacts with water vapor high in the atmosphere to form these corrosive clouds. If you could somehow fly through them, the acid would eat through almost any material. Rain falls from these clouds, droplets of sulfuric acid, but the surface is so hot that the rain evaporates long before reaching the ground. There's never any rain on Venus's surface, only this perpetual acid drizzle that boils away in the superheated lower atmosphere. These thick clouds create a powerful greenhouse effect. Sunlight penetrates the clouds and warms the surface, but the heat cannot escape back to space. The dense atmosphere, made of 96% carbon dioxide, traps the infrared radiation, causing temperatures to build and build until they reach equilibrium at an astonishing level. The surface temperature on Venus is about 900 degrees Fahrenheit. That's hot enough to melt lead and zinc, hot enough to make rock glow faintly red, and this temperature is nearly uniform across the entire planet. It's the same temperature at the equator as at the poles, the same at noon as at midnight. The thick atmosphere distributes heat so efficiently that there's barely any temperature variation anywhere on the planet. The atmospheric pressure at the surface is crushing, 92 times greater than Earth's atmospheric pressure at sea level. Standing on Venus's surface would feel like being 3,000 feet underwater on Earth. This pressure combined with the heat makes Venus's surface one of the most hostile environments imaginable. Despite the clouds, some sunlight does filter through to the surface, enough to see by. The light would have an orange-reddish tint from filtering through all that atmosphere. The sky would glow rather than appearing as a distinct sun or stars. It would be perpetual dim twilight, hot and oppressive, with the wind blowing gently at the surface, about walking speed, though that wind becomes a roaring hurricane in the upper atmosphere. Now, let's look at what we know of the surface beneath those clouds. We can't see it directly from space, but radar can penetrate the clouds and map the terrain. Several Soviet Venera landers reached the surface in the 1970s and 80s, and the Magellan spacecraft mapped Venus with radar from orbit in the early 1990s. What they revealed was a world dominated by volcanism. About 80% of Venus's surface is covered by smooth volcanic plains, ancient lava flows that spread across vast areas. There are more volcanoes on Venus than on any other planet in the solar system. Over 1,600 major volcanoes identified, and likely many more smaller ones. Some of these volcanoes are enormous. Mount Mons rises about 5 miles above the surrounding plains. Though the lack of plate tectonics means volcanic structures don't grow as tall on Venus as they do on smaller worlds like Mars. Still, these are impressive mountains of cooled lava, monuments to a volcanic past. Scientists believe Venus experienced a global resurfacing event about 300 to 500 million years ago. Some catastrophic period of intense volcanism buried the older surface under fresh lava, essentially giving the planet a new skin. We don't see impact craters older than this because they were all buried. The craters we do see are relatively young, formed after this resurfacing event. Why did this happen? It may be related to the lack of plate tectonics. On Earth, heat escapes continuously through volcanic activity at plate boundaries. Venus, with no plate tectonics, may build up heat in its interior until it reaches a critical point, then releases it all at once through planet-wide volcanism. This might happen periodically, giving Venus a cycle of geological activity very different from Earth's steady-state system. Besides the volcanic plains and mountains, Venus has other fascinating features. There are tesserae, regions of highly deformed terrain with ridges and valleys crisscrossing in complex patterns. These may be ancient crustal regions that somehow avoided the resurfacing event. There are coronae, strange circular or oval features surrounded by ridges and fractures, possibly caused by plumes of hot material rising from deep within Venus, pushing up the surface and then collapsing. And there are arachnoids, spidery features with a central volcano or corona surrounded by radiating fractures, looking like a splash frozen in stone. Venus also has long, winding channels carved by ancient lava flows, and vast plateaus that rise miles above the surrounding plains. There's Ishtar Terra in the northern highlands, containing Maxwell Montes, the highest mountains on Venus, rising 7 miles above mean planetary radius. Some scientists believe Venus may have had oceans in the distant past. Early in its history, Venus might have been more Earth-like, with liquid water on its surface. But as the sun grew brighter and Venus's atmosphere thickened, a runaway greenhouse effect evaporated any oceans, and the water vapor eventually escaped to space or was locked into rocks. Now Venus is desiccated, any water it once had long gone. This raises fascinating questions about planetary evolution and habitability. Venus and Earth started very similarly. They formed in the same region of the solar nebula, from the same materials, with similar sizes and compositions. Yet Earth became a water world teeming with life, while Venus became an inferno. The difference may be as simple as distance from the Sun. Venus was just close enough that the extra solar heating triggered a runaway greenhouse effect, while Earth was just far enough to avoid this fate. It's humbling to realize how narrow the habitable zone is, how fine the line between a living world and a dead one. Venus has no moons, no magnetic field to speak of, and rotates so slowly that it presents nearly the same face to the Sun throughout its year. The solar wind strikes Venus's atmosphere directly, stripping away atoms of gas slowly over time. Despite its harsh conditions, there's ongoing interest in Venus. Some scientists have speculated that high in the atmosphere, around 30 miles above the surface where temperatures and pressures are more moderate, conditions might be suitable for microbial life. Certain chemical signatures detected in the atmosphere have sparked debates about possible biological activity, though nothing is confirmed and most scientists favor non-biological explanations. Future missions may send balloons or airships to float in Venus's atmosphere, studying the clouds and searching for any signs of chemistry that might hint at life. The surface remains incredibly challenging to explore. The longest any lander has survived on the surface was just over 2 hours before the heat and pressure destroyed it. As we prepare to leave Venus, take a moment to appreciate this beautiful, terrible world. She shines so brightly in Earth's sky, a beacon of light in the evening or morning, a planet that captivated ancient astronomers and still captures our imagination. But beneath that serene beauty lies a cautionary tale about greenhouse gases, atmospheric evolution, and the delicate balance that makes a planet habitable. Our next stop is home, a blue marble in the black of space, a world of water and life and infinite wonder. Earth, the blue marble. We're drifting away from Venus now, traveling outward to the third planet from the Sun, and as it comes into view, you might feel your heart swell with recognition and love. There it is, Earth, our home. From this distance in space, about 100,000 miles away, Earth appears as a brilliant blue and white sphere against the darkness. It's so beautiful it almost brings tears to your eyes. The deep blue of the oceans, the swirling white clouds, the brown and green of continents, all blending together in a display of color and life unlike anything else in the solar system. Earth is unique. There's no other world we know of quite like it. A world where water exists in all three states: liquid, solid, and vapor. A world with an active geology that continuously recycles its surface. A world wrapped in a protective atmosphere. And most remarkably, a world absolutely teeming with life. Let's drift closer, slowly, taking our time to appreciate this precious planet. Earth orbits the Sun at an average distance of 93 million miles, taking 365.25 days to complete one orbit. This is the definition of 1 year, the time our world takes to circle our star. We rotate once every 24 hours, giving us our familiar cycle of day and night, light and darkness, warmth and cool. Earth is about 7,900 miles in diameter, making it the largest of the terrestrial planets and the fifth largest planet overall. Our mass and size give us a surface gravity that shaped the evolution of life here. Strong enough to retain a thick atmosphere, but gentle enough to allow the development of complex organisms. Now observe the colors. The overwhelming blue is water. Oceans cover about 71% of Earth's surface, holding about 97% of all water on the planet. These oceans are not just pools of water, they're dynamic systems, constantly moving, circulating, exchanging heat and gases with the atmosphere. Ocean currents flow like rivers within the sea, carrying warm water from the equator toward the poles and cold water from the poles back toward the equator. The Gulf Stream in the Atlantic, the Kuroshio Current in the Pacific. These great currents moderate climate, making some regions warmer or cooler than they would otherwise be. The oceans are also home to the majority of life on Earth, from microscopic plankton that form the base of the food chain to the largest animals ever to exist, the blue whales. The oceans support an incredible diversity of organisms: coral reefs, kelp forests, deep-sea vents. Each habitat hosts communities adapted to their specific conditions. And beneath the ocean surface lies fascinating geology. Mid-ocean ridges where new crust is continuously created as magma wells up from the mantle. Deep trenches where old crust is swallowed back into the earth. Seamounts, underwater volcanoes, some rising nearly to the surface. The ocean floor is as varied and dynamic as the continents, a hidden landscape of mountains and valleys. Now look at the white swirling patterns. These are clouds, water vapor condensed into tiny droplets or ice crystals, forever moving across the sky. Clouds form when moist air rises and cools, causing the water vapor to condense. They're part of Earth's water cycle, the continuous movement of water between ocean, atmosphere, and land. Evaporation lifts water from the oceans into the air. Wind carries the moisture-laden air over land. As the air rises and cools, clouds form, and eventually rain or snow falls, replenishing rivers and lakes, soaking into soil and groundwater. The water then flows back to the oceans, and the cycle continues, year after year, eon after eon. Clouds also play a crucial role in Earth's temperature balance. Bright white clouds reflect sunlight back to space, cooling the planet, but they also trap heat radiated from the surface, warming it. The balance between these effects, along with other factors, helps maintain Earth's moderate temperatures. See those brown and green masses? Those are continents, the land above sea level. Earth has 7 continents: Asia, Africa, North America, South America, Antarctica, Europe, and Australia. They cover about 29% of the surface but host much of the visible diversity of landscapes and life. Mountains rise in majestic chains: the Himalayas, the Andes, the Rockies, the Alps. These mountains were pushed up by the motion of tectonic plates, the massive slabs of crust that float on Earth's mantle and slowly shift over millions of years. Earth is the only planet in the solar system with plate tectonics. Our crust is broken into about a dozen major plates and several smaller ones. These plates move at about the speed your fingernails grow, just an inch or 2 per year. But over millions of years, this motion reshapes the entire planet. Where plates collide, one may slide beneath the other in a process called subduction, creating deep ocean trenches and chains of volcanoes, or both plates may crumple together, pushing up mountains. The Himalayas formed when the Indian plate collided with the Eurasian plate and continue to rise slowly today. Where plates pull apart, magma rises to fill the gap, creating new crust. This happens at mid-ocean ridges, where the seafloor is spreading, and also in rift valleys on land, where plates slide past each other. Earthquakes occur as the rocks grind and suddenly slip. The San Andreas Fault in California is a famous example of this transform boundary. This tectonic activity does more than shape the landscape. It's crucial for maintaining Earth's habitability. Plate tectonics helps regulate the carbon cycle. Carbon dioxide from the atmosphere dissolves in rain, reacts with rocks, and is carried to the oceans where it forms carbonate minerals. These minerals get subducted into the mantle and are eventually released again through volcanic activity. This long-term cycle helps stabilize Earth's climate over geological time. Now look at the greens and browns on land. The green is vegetation, plants that cover vast areas of the continents, tropical rainforests near the equator, temperate forests in the mid-latitudes, boreal forests in the far north, grasslands and savannas, agricultural fields where humans grow crops. Plants were the first organisms to colonize land, about 450 million years ago. They transformed Earth's atmosphere by producing oxygen through photosynthesis, making the air breathable for animals. Today, plants on land and phytoplankton in the oceans continue producing oxygen and absorbing carbon dioxide, maintaining the atmospheric balance that supports life. The brown and tan areas are deserts and bare rock. The Sahara in Africa, the Arabian Desert, the Gobi in Asia, the Australian outback. These dry regions receive little rainfall but still support specialized life forms adapted to arid conditions. Notice the white caps at the top and bottom of the globe. These are the polar ice caps. The Arctic in the north is mostly frozen ocean, sea ice floating on the Arctic Ocean. The Antarctic in the south is a massive continent buried beneath ice sheets up to 3 miles thick. These ice caps play crucial roles in Earth's climate. They reflect sunlight, helping keep the planet cool. They store fresh water. About 70% of Earth's fresh water is locked in ice, mostly in Antarctica, and they drive ocean currents as cold, salty water from the poles sinks and flows toward the equator. Earth has a magnetic field generated by the churning of molten iron in our outer core. This magnetic field extends far into space, creating a protective bubble called the magnetosphere. The magnetosphere deflects most of the solar wind, protecting our atmosphere from being stripped away and shielding life on the surface from harmful radiation. When charged particles from the solar wind do interact with Earth's magnetic field near the poles, they create the auroras, shimmering curtains of light in the night sky, green and red and purple, dancing and waving as particles collide with atmosphere molecules. Earth's atmosphere is precious and complex. It's about 78% nitrogen, 21% oxygen, and small amounts of other gases including carbon dioxide, water vapor, and noble gases. This mixture is perfect for life as we know it. The oxygen allows animals to breathe and supports combustion. The nitrogen is relatively inert but essential for making proteins. Carbon dioxide, though a trace gas, is vital for plants and helps regulate temperature through the greenhouse effect. The atmosphere also protects us. The ozone layer, high in the stratosphere, absorbs ultraviolet radiation from the sun that would otherwise damage DNA and harm living things. The atmosphere as a whole acts as a blanket, moderating temperature swings between day and night, and it creates weather driven by uneven solar heating and Earth's rotation. The atmosphere circulates in complex patterns. Warm air rises at the equator and flows toward the poles. Cold air sinks at the poles and flows toward the equator. These circulations, modified by the Coriolis effect from Earth's rotation, create the trade winds, westerlies, and polar easterlies, the major wind patterns that shape climate zones. Weather systems develop where warm and cold air masses meet. Hurricanes form over warm tropical oceans, drawing energy from the water's heat. Thunderstorms develop when warm. Moist air rises rapidly and cools. Blizzards occur when cold air masses bring heavy snow. These weather events, while sometimes destructive, are part of Earth's dynamic atmospheric system, redistributing heat and moisture around the planet. Now, cast your gaze to the Moon. Earth's natural satellite orbits us at an average distance of about 239,000 miles, taking 27.3 days to complete one orbit. The Moon is large for a satellite, about 1/4 Earth's diameter, and it profoundly influences our planet. The Moon's gravity creates tides in Earth's oceans, causing the water to bulge on the side facing the Moon and on the opposite side. As Earth rotates, different areas experience high and low tides roughly twice a day. Tides don't just affect the oceans. They create tidal pools, unique coastal ecosystems. They mix nutrients in coastal waters. Some scientists believe tides were important for the evolution of life, creating environments where organisms could adapt to both aquatic and terrestrial conditions. The Moon also stabilizes Earth's axial tilt. Our planet is tilted 23.5 degrees relative to our orbital plane. This tilt gives us seasons, as different hemispheres receive more or less direct sunlight throughout the year. Without the Moon's stabilizing gravitational influence, Earth's tilt would vary chaotically over millions of years, causing extreme climate instability. The Moon helps keep our climate predictable and stable. The Moon formed about 4.5 billion years ago, most likely from debris ejected when a Mars-sized object collided with the young Earth. This catastrophic impact melted both bodies, and material thrown into orbit eventually coalesced into the Moon. Evidence from lunar rocks brought back by Apollo astronauts supports this giant impact hypothesis. Now, think about life on Earth. Everywhere you look, life thrives in the oceans, on land, in the air, even deep underground and in the atmosphere, from bacteria to blue whales, from fungi to giant sequoia trees. Earth hosts millions of species in countless ecosystems. Life has existed on Earth for at least 3.5 billion years, almost as long as the planet itself. The first life was simple, single-celled organisms over billions of years through evolution by natural selection. life diversified and became more complex. Photosynthetic bacteria and later plants transformed the atmosphere by producing oxygen. Animals evolved to breathe this oxygen. Life colonized every available habitat, from the deep ocean to mountain peaks, from polar ice to desert sands, from the depths of caves to the canopy of rainforests. Humans are a very recent addition. Our species, Homo sapiens, has existed for only about 300,000 years, a mere blink in Earth's history. Yet in that brief time, we've spread across the globe, developed technology, built civilizations, and gained the ability to study and understand our planet and the universe beyond. Earth is resilient. It has endured ice ages and warming periods, asteroid impacts and volcanic eruptions, mass extinctions and recoveries. Through it all, life has persisted, adapted, and flourished. But Earth is also fragile. The conditions that make it habitable, the liquid water, the oxygen-rich atmosphere, the moderate temperatures, are maintained by delicate balances. Change those balances too much or too quickly, and the results could be catastrophic for many species, including us. As we prepare to leave Earth and continue our journey, take a long, loving look at this beautiful blue marble. This is our home, the only planet we know of that harbors life, the only world in the vast universe where we can live without artificial support. Treasure it, protect it, and carry its image in your heart as we explore the other worlds of our solar system, worlds that remind us just how special and precious Earth truly is. Our next stop is Earth's neighbor to the outside, a world that has captivated human imagination for centuries, a rusty red planet that may once have had rivers and oceans, a world that might still harbor life hidden beneath its surface. Let's visit Mars. Mars, the red planet. We're leaving Earth behind now, traveling outward past the Moon's orbit, through the space between our world and the next, and there, about 50 million miles away at its closest approach, we see Mars. Even from a distance, Mars is unmistakably red, not the bright red of fresh paint, but a dusky, rusty red-orange, the color of iron oxide, of weathered metal, of ancient deserts. Mars is named after the Roman god of war, and that red color, reminiscent of blood, seems fitting. But Mars is not a violent world. It's a cold, quiet planet, a place of stillness and vast landscapes, where dust storms can engulf the entire globe and ancient volcanoes stand as monuments to a more active past. Mars is about half the diameter of Earth, just over 4,000 miles across. It's much less massive, only about 11% of Earth's mass, so its surface gravity is only 38% of Earth's. If you weigh 100 pounds on Earth, you'd weigh only 38 pounds on Mars. You could jump nearly 3 times as high. Mars orbits the Sun at an average distance of about 142 million miles, taking 687 Earth days to complete one orbit. That's almost 2 Earth years for one Martian year. But a Martian day is very similar to Earth's. Mars rotates once every 24 hours and 37 minutes. This similarity makes Mars feel somewhat familiar. A world with day-night cycles much like our own, Mars is also tilted on its axis, about 25 degrees, very similar to Earth's 23.5-degree tilt. This means Mars has seasons much like Earth. However, Mars's elliptical orbit makes its seasons more variable. When Mars is closest to the Sun during southern summer, that season is short and hot. When it's farthest during northern summer, that season is longer and cooler. Let's drift closer and examine this fascinating world. The first thing you notice is the pervasive red color. Mars gets its color from iron oxide, essentially rust. in the dust and rocks on its surface. Iron on the surface oxidized long ago when Mars had a thicker atmosphere, and now the entire planet is coated in this rusty material. But not everything is red. The polar ice caps shine white, made of water ice and, in winter, dry ice or frozen carbon dioxide. Dark patches reveal areas where the dust has been blown away, exposing underlying rocks. And there are lighter streaks and patterns created by dust devils and windstorms continually rearranging the thin layer of dust. Mars has some of the most spectacular geological features in the solar system. Look there. In the Tharsis region near the equator, rising majestically above the surrounding plains are the Tharsis Montes, 3 enormous volcanoes, Asteroid Mons, Olympus Mons, and Asteroid Mons. Each stands about 10 to 12 miles high, but they're dwarfed by Olympus Mons just to the northwest. Olympus Mons is the tallest volcano and tallest mountain in the entire solar system. It rises about 13.6 miles above the surrounding plains, nearly 2.5 times the height of Mount Everest. Its base is about 370 miles across, roughly the size of the state of Arizona. If you stood at the base, you couldn't see the summit because it would be beyond the horizon. The caldera at the top contains multiple collapse craters, evidence of past eruptions. Olympus Mons is a shield volcano formed by countless lava flows over billions of years. Mars's lower gravity allows mountains to grow taller before they collapse under their own weight, and the lack of plate tectonics means a volcano can remain over a hotspot indefinitely, continuing to build upward. Olympus Mons is currently dormant, but it may not be extinct. It could erupt again if Mars's interior is still active enough. Now shift your gaze to the other side of Mars. Stretching across the equator is an enormous canyon system called Valles Marineris. This is the largest canyon system in the solar system, about 2,500 miles long, up to 400 miles wide in places, and up to 7 miles deep. Valles Marineris makes Earth's Grand Canyon look tiny by comparison. If it were on Earth, it would stretch all the way across the United States from coast to coast. The canyon system formed from a combination of tectonic fracturing and erosion. As the Tharsis region swelled from volcanic activity, it stretched and cracked the crust, creating the initial faults. Over time, landslides, wind erosion, and possibly water flow widened and deepened the canyons. If you could stand at the rim and look across, the far wall would be beyond sight, lost in the hazy distance. The walls are layered with different rock strata, a geological record of Mars's history. In some places, the walls show evidence of past groundwater seepage, with minerals deposited in layers. Mars has a thin atmosphere, less than 1% the density of Earth's. It's mostly carbon dioxide, 95%, with small amounts of nitrogen and argon. This thin atmosphere provides little protection from solar radiation and creates little greenhouse warming. Surface temperatures average about -80 degrees Fahrenheit, though they can reach a relatively comfortable 70 degrees at the equator in summer, or plunge to -200 degrees at the poles in winter. The low atmospheric pressure means liquid water can't exist on the surface. Water would instantly boil or freeze, but ice is stable, and there's abundant water ice on Mars. The polar caps are the most obvious ice deposits. The northern cap is mostly water ice, about 2 miles thick and about 600 miles across. It persists year-round. In winter, a layer of dry ice about 3 feet thick forms on top, then sublimes away in summer. The southern cap is smaller and sits on higher terrain. It's also mostly water ice but retains a layer of dry ice year-round because it doesn't get as warm. Beyond the polar caps, ice exists underground across much of Mars. Spacecraft have detected ice just beneath the surface at middle and high latitudes, sometimes only inches deep. This ice is a resource that future explorers could use for drinking water, growing food, or making rocket fuel. Now, here's where Mars becomes truly intriguing from a scientific perspective. There's abundant evidence that liquid water once flowed on Mars's surface. Look closely at the ancient highlands. You'll see branching networks of valleys that look remarkably like river drainage systems on Earth. These valley networks date back over 3.5 billion years. They must have been carved by flowing water. See those flat plains in the northern lowlands? Some scientists believe these were once ocean basins. Ancient shoreline features have been tentatively identified, though the evidence is debated. Scattered across Mars are what appear to be ancient lake beds, flat areas with delta-like features where rivers once deposited sediment. Spacecraft have found minerals on the surface that form only in the presence of liquid water: clays, sulfates, carbonates. These minerals tell a story of a wetter past. Gullies on crater walls and canyon slopes look fresh, possibly formed recently by seasonal flows of briny water or by dry landslides. Some features called recurring slope lineae appear and fade with the seasons, possibly caused by seeping salty water, though this remains uncertain. All this evidence points to a dramatically different Mars in the distant past. Billions of years ago, Mars may have had a thicker atmosphere and warmer temperatures. Rain might have fallen, rivers flowed, lakes and perhaps oceans existed. The planet was more Earth-like, at least for a while. What happened? Why did Mars lose its water and become the cold desert it is today? Mars is smaller than Earth, so its interior cooled faster. As the core cooled, Mars lost its global magnetic field. Earth's magnetic field protects our atmosphere from the solar wind, but Mars's atmosphere became exposed. Over millions of years, the solar wind stripped away Mars's atmosphere, particle by particle. As the atmosphere thinned, the greenhouse effect weakened, temperatures dropped, and liquid water could no longer exist. Any remaining water froze or retreated underground. This transformation took hundreds of millions of years, but eventually Mars changed from a potentially habitable world to the frozen desert we see today. But here's the exciting question. During that early period when liquid water existed, could life have emerged on Mars? If so, could it have survived underground, in aquifers or deep rocks, where liquid water might still exist and conditions remain stable? We don't know yet. Mars rovers have been searching for signs of past life, analyzing rocks and soil for organic molecules or other biosignatures. So far, no definitive evidence of life has been found, but the search continues. Future missions will return samples to Earth for detailed study. Humans may one day explore Mars directly, drilling deep below the surface, searching caves and underground water sources, looking for answers to one of the most profound questions we can ask. Are we alone, or has life emerged elsewhere? Mars has two small moons, Phobos and Deimos. They're tiny, irregularly shaped, probably captured asteroids. Phobos is the larger, about 14 miles across, and orbits very close to Mars, circling the planet in just 7.5 hours. It's so close and orbits so fast that from Mars's surface, you'd see it rise in the west and set in the east, twice a day. Tidal forces are gradually pulling Phobos closer, and in about 50 million years it will either crash into Mars or be torn apart by tidal forces, creating a temporary ring. Deimos is smaller, about 8 miles across, and orbits farther out, taking 30 hours to circle Mars. From the surface, it would appear as a bright star slowly crossing the sky. Both moons are dark and heavily cratered, ancient bodies that have witnessed Mars's transformation from a warmer, wetter world to the cold desert it is today. As we prepare to leave Mars, take one last look at this rusty world, this planet of dust devils and dust storms, of towering volcanoes and vast canyons, of ancient riverbeds and frozen ice caps. Mars reminds us that planets can change dramatically over time. It shows us that habitability can be lost. But it also offers hope, the possibility that life might have existed there once, or might still exist in hidden refuges below the surface. Mars is our next frontier, a world close enough to reach, similar enough to understand, yet different enough to challenge us. Now, let's continue outward, passing through a region of scattered rocks and metal, remnants from the solar system's formation that never coalesced into a planet. But don't imagine a dense field of rocks where collisions are constant, like in science fiction movies. The asteroid belt is actually mostly empty space. The asteroids are spread out over an enormous volume, and the distance between even neighboring asteroids is typically millions of miles. You could fly through the asteroid belt without seeing a single asteroid out your window. Still, there are many objects here, and they tell an important story about planetary formation. The asteroid belt occupies the region from about 2.2 astronomical units to about 3.2 astronomical units from the Sun. That's roughly 205 million miles to 300 million miles. It's a broad band, millions of miles thick and billions of miles in circumference. Scientists estimate there are over 1 million asteroids larger than a half-mile across, millions more smaller ones, and countless tiny rocks and dust particles. Together, all the mass in the asteroid belt amounts to only about 4% of the Moon's mass. If you could gather all the asteroids together, they'd form a body smaller than our Moon. These asteroids are leftovers, pieces that never assembled into a planet. When the solar system was forming, this region should have produced another planet between Mars and Jupiter, but Jupiter's powerful gravity disrupted the formation process. Its gravitational influence stirred up the orbital velocities of objects in this region, causing collisions to become destructive rather than constructive. Instead of sticking together to form larger bodies, planetesimals smashed into each other, breaking apart, preventing a planet from forming. So the asteroid belt is a record of what might have been, a planetary ghost, forever scattered. Asteroids come in different types based on their composition. The most common are carbonaceous or C-type asteroids, dark and carbon-rich, likely similar to the material from which planets formed. About 75% of asteroids are C-type. Then there are silicate or S-type asteroids, made of rocky silicate materials mixed with some iron. These make up about 17% of asteroids and are more common in the inner belt, closer to the Sun. Finally, there are metallic or M-type asteroids, composed primarily of iron and nickel, probably fragments of the cores of larger bodies that were disrupted by collisions. These are much less common but incredibly valuable for their metal content. Asteroids range in size from dust grains to objects hundreds of miles across. Most are irregular chunks of rock or metal, their shapes determined by collisions and gravitational interactions rather than by their own gravity pulling them into spheres. Now, among all these asteroids, one stands out as truly special. Let's visit the largest object in the asteroid belt. There it is, growing in our view, Ceres. Ceres is unique. It's so large, about 580 miles in diameter, that its gravity has pulled it into a nearly spherical shape. It's classified as a dwarf planet, the only one in the inner solar system. Ceres contains about 25 to 40% of the total mass of the entire asteroid belt, If you combined several of the next largest asteroids, they still wouldn't equal Ceres in mass. As we approach Ceres, you can see it's not just a rock. Its surface is grey and heavily cratered, pockmarked by billions of years of impacts. But some features stand out dramatically. Look there, bright white spots shining against the darker terrain. The most famous of these bright regions is Indicator Crater, a young impact crater about 57 miles across. Inside the crater floor are brilliant white patches that reflect sunlight intensely. When the Dawn spacecraft visited Ceres from 2015 to 2018, it revealed that these bright spots are salt deposits, likely sodium carbonate and other minerals. They formed when briny water or ice beneath the surface was exposed by impacts and then sublimed away, leaving behind concentrated salts. This suggests something remarkable. Ceres has, or had, a subsurface ocean of salty water. It's possible that a global ocean of briny water exists beneath Ceres's surface, trapped between a rocky core and an icy outer shell. Heat from radioactive decay in the core might keep this water liquid. If this ocean exists, Ceres would join a small club of ocean worlds in our solar system, including Europa, Enceladus, and others. And where there's liquid water, there's potential, however remote, for life. Ceres also has a very thin atmosphere, technically an exosphere, created when ice sublimates from the surface when warmed by the sun. Water vapor escapes into space or temporarily hovers around the dwarf planet before freezing back onto the surface. Some craters on Ceres show evidence of past cryovolcanism, where slushy ice, water, and salts erupted from below, flowing like lava and forming domes and mountains. One feature, Olympus Mons, rises about 13,000 feet and appears to be a cryovolcanic dome, formed within the last few million years, geologically very recent. The interior structure of Ceres likely consists of a rocky core, a layer of water ice mixed with minerals, and a thin, dusty crust. Over its history, the interior has differentiated, with heavier materials sinking toward the center and lighter materials rising. Studying Ceres helps us understand how planets form and differentiate. It's large enough to have undergone some of the same processes as planets, yet small enough that its evolution was different, halted early by its location and mass. As we prepare to leave the asteroid belt, take a moment to appreciate these ancient remnants. Each asteroid is a time capsule, preserving material from the solar nebula, largely unchanged since the solar system's formation. By studying them, we learn about the building blocks of planets, including Earth. Asteroids have also played a dramatic role in shaping planetary surfaces. Impacts from asteroids have cratered the Moon, scarred Mercury and Mars, and occasionally struck Earth, sometimes with catastrophic effects. The asteroid impact 66 million years ago that helped end the age of the dinosaurs reminds us that these ancient rocks can profoundly affect life on Earth. But asteroids also may have delivered water and organic molecules to the early Earth, helping to create the conditions for life to begin. They are both threat and gift, destroyer and creator. Now, let's continue outward, beyond the asteroid belt, toward the realm of the giant planets. The temperature drops, the sun shrinks to a bright but distant star, and before us looms the largest planet in the solar system, a world of swirling clouds and dozens of moons, a miniature solar system unto itself. Jupiter, king of the planets. We're crossing into the outer solar system now, leaving behind the rocky inner planets and the asteroid remnants, and ahead of us, growing larger with every moment, is Jupiter. Even from this distance, Jupiter dominates the view. It's enormous, utterly enormous, the largest planet in our solar system, a gas giant so vast that all the other planets combined could fit inside it with room to spare. Jupiter is named after the king of the Roman gods, and it's fitting. This planet reigns supreme, its powerful gravity shaping the orbits of countless asteroids and comets, its magnetosphere extending millions of miles into space, its family of moons like a court surrounding a celestial monarch. As we drift closer, details emerge. Jupiter is a world of clouds, thick bands of color wrapping around the planet: tan, white, brown, orange, red, all blending and swirling in complex patterns. Jupiter is about 88,800 miles in diameter at its equator, more than 11 times Earth's diameter. If Earth were the size of a grape, Jupiter would be the size of a basketball. Jupiter is so massive that it contains more than twice the mass of all the other planets combined. Yet despite this enormous mass, Jupiter's density is low. It's made primarily of hydrogen and helium, the lightest elements, with only a small rocky core. If there were an ocean large enough, Jupiter would float, though not as easily as Saturn. Jupiter orbits the Sun at an average distance of about 484 million miles, taking nearly 12 Earth years to complete one orbit. But its day is remarkably short. Jupiter rotates faster than any other planet, spinning once in just under 10 hours. This rapid rotation causes the planet to bulge noticeably at the equator and flatten at the poles, giving Jupiter an oblate spheroid shape. Let's examine Jupiter's atmosphere as we approach. The cloud bands you see are organized into zones and belts. The lighter zones are regions of rising gas, where ammonia ice forms bright white clouds at high altitudes. The darker belts are regions of sinking gas, where you're seeing deeper into the atmosphere to warmer layers, and the clouds contain compounds that give them brown and tan colors. These bands circle the entire planet, driven by Jupiter's rapid rotation and powerful convection currents. Jet streams at the boundaries between zones and belts blow at hundreds of miles per hour, faster than the strongest hurricanes on Earth. The atmosphere is turbulent, constantly churning. Storms form and dissipate. Eddies and vortices swirl in the cloud tops. The entire atmosphere is a fluid in motion, with no solid surface beneath to slow it down. And then there's the Great Red Spot. Look there, in the southern hemisphere, a massive oval storm, rusty red-orange in color, big enough to swallow Earth whole. This is the Great Red Spot, the largest and longest-lasting storm in the solar system. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise in the southern hemisphere, driven by high-pressure systems. It's essentially a gigantic, persistent hurricane. Winds in the storm reach over 400 miles per hour at the edges, and the storm rises about 5 miles above the surrounding clouds. What's remarkable is how long it's lasted. Astronomers have been observing the Great Red Spot for at least 350 years, since the invention of the telescope. It may be even older. For centuries, this storm has raged, fed by Jupiter's internal heat and the energy from its rapid rotation. But the Great Red Spot is shrinking. In the 1800s, it was about 3 times wider than Earth. Now it's only about 1.3 times Earth's diameter. Why it's shrinking and whether it will eventually dissipate is unknown. Perhaps we're witnessing the slow death of a centuries-old storm. Or perhaps it will stabilize at a smaller size and persist for centuries more. Besides the Great Red Spot, Jupiter hosts many other storms. There have been smaller red spots, white ovals, and brown barges, each a storm system in its own right. The atmosphere is constantly changing, with new storms forming and old ones merging or dissipating. Now, what lies beneath these clouds? We can't see through them, but spacecraft and theoretical models give us clues. Below the visible cloud tops, pressure and temperature increase rapidly. The hydrogen gas becomes denser and hotter. About 600 miles down, the pressure becomes so great that hydrogen transitions from a gas to a liquid, though there's no distinct surface, just a gradual transition. Descending further, perhaps 10,000 to 12,000 miles deep, the pressure becomes so immense that hydrogen transforms into a strange state called metallic hydrogen. In this state, hydrogen atoms are squeezed so tightly that electrons are stripped away and move freely, making the hydrogen conduct electricity like a metal. This metallic hydrogen layer is thought to extend halfway to Jupiter's center. At the core, there may be a solid or slushy region composed of rock, metal, and ice, perhaps 10 to 20 times Earth's mass. But even this is uncertain. Some models suggest the core might have partially dissolved into the surrounding layers. What's certain is that Jupiter's interior is hot. The planet radiates more heat into space than it receives from the Sun. Jupiter is still slowly contracting from its formation, and this gravitational contraction generates heat, warming the interior and contributing to the atmospheric dynamics. Jupiter's magnetic field is the strongest of any planet, about 14 times stronger than Earth's. It's generated by the motion of metallic hydrogen in the interior, creating a powerful dynamo effect. The magnetosphere extends millions of miles into space, all the way past Saturn's orbit on the side facing the Sun, and it stretches even farther in the opposite direction, creating a long tail. This magnetosphere traps charged particles from the solar wind, creating intense radiation belts, far more dangerous than Earth's Van Allen belts. Any spacecraft or future astronauts venturing near Jupiter must contend with this radiation. The magnetosphere also interacts with Jupiter's moons, particularly Io. Volcanic gases from Io become ionized and trapped in the magnetosphere, forming a donut-shaped cloud of plasma called the Io plasma torus. This interaction creates powerful auroras at Jupiter's poles, shimmering curtains of light far more intense than Earth's auroras. Speaking of moons, Jupiter has at least 95 known moons, and more are discovered periodically. Most are small, irregular captured asteroids, but 4 moons stand out, so large and interesting that they're called the Galilean moons after Galileo Galilei, who discovered them in 1610 with his early telescope. Let's visit each of the Galilean moons briefly. First, Io. Look at it there, a world slightly larger than our moon, appearing yellowish and orange with patches of red, white, and black. Io is the most volcanically active body in the solar system. Its surface is constantly being resurfaced by volcanic activity, with hundreds of active volcanoes erupting sulfur and sulfur dioxide. Why so much volcanism? Io's orbit is slightly elliptical, and as it orbits Jupiter, tidal forces from Jupiter and the other Galilean moons flex and squeeze Io, generating enormous heat through friction. This tidal heating melts rock in Io's interior, driving the volcanism. Volcanic plumes on Io can shoot 250 miles above the surface, visible from space. Lava flows spread across plains. The surface is young, with no impact craters visible because volcanic activity erases them quickly. Next is Europa, an icy moon slightly smaller than our moon. Europa appears smooth and bright, covered in water ice crisscrossed by brownish streaks and cracks. The surface is relatively crater-free, suggesting it's geologically young, constantly being resurfaced. Beneath the ice, scientists believe there's a global ocean of liquid water, perhaps 60 miles deep. Tidal heating from Jupiter keeps this ocean from freezing. Despite Europa's distance from the Sun, the ice shell on top might be only 10 to 15 miles thick, possibly thinner in some areas. This subsurface ocean makes Europa one of the most promising places to search for life beyond Earth. There might be hydrothermal vents on the ocean floor, similar to those on Earth where life thrives in complete darkness. Future missions may send landers to drill through the ice or submarines to explore the ocean, searching for signs of life. Then there's Ganymede, the largest moon in the solar system, even larger than the planet Mercury, about 3,300 miles in diameter. Ganymede is unique because it has its own magnetic field, the only moon known to have one. This magnetic field creates a miniature magnetosphere within Jupiter's massive magnetosphere. Ganymede's surface is a mix of two terrain types: dark, ancient, heavily cratered regions, and bright, younger regions covered with grooves and ridges. These grooved terrains formed from tectonic activity, where the icy crust stretched and fractured. Like Europa, Ganymede probably has a subsurface ocean, buried deeper beneath a thicker ice shell. It might even have multiple layers of ice and water, a club sandwich of oceans and ice. Finally, Callisto, the outermost Galilean moon, about the same size as Mercury. Callisto's surface is ancient, dark, and heavily cratered, showing little geological activity. It's essentially a fossil, preserving a record of impacts dating back billions of years. One enormous impact structure, Valhalla, is a multi-ring basin over 1,800 miles across, visible as concentric bright rings. Callisto also likely has a subsurface ocean, though less certain than Europa's or Ganymede's. Its interior is less differentiated than the other Galilean moons, a mixture of rock and ice rather than separated layers. Together, the Galilean moons are worlds in their own right, each fascinating, each with unique characteristics. They orbit Jupiter like a miniature solar system, locked in gravitational resonance. Their orbits synchronized in a complex dance that has persisted for billions of years. Jupiter also has faint rings, much less prominent than Saturn's, but rings nonetheless. They're made of dust ejected from Jupiter's small inner moons by micrometeorite impacts. The rings are thin and faint, visible only in backlit images, a delicate halo around the giant planet. As we prepare to leave Jupiter, take a moment to appreciate this colossal world. Jupiter is a giant, a planet so massive that if it were much larger, it would begin to fuse hydrogen and become a star. It shaped the early solar system, influencing the orbits of asteroids and possibly preventing another planet from forming. Jupiter's gravity has also protected the inner solar system to some extent, deflecting or capturing comets and asteroids that might otherwise threaten Earth. We owe Jupiter a debt, this giant guardian, quietly shaping the neighborhood in which we live. Now, we continue outward, toward a planet whose beauty is legendary, whose rings are the most spectacular sight in the solar system. Saturn, the ringed jewel. We're drifting farther from the sun now, deeper into the cold outer reaches, and ahead of us, suspended in the blackness like a jewel in a velvet case, is Saturn. At first, it's just a bright point, but as we approach, details emerge, and you gasp softly, because there, shining in the faint sunlight, are the rings. Saturn's rings are the most magnificent, awe-inspiring sight in the solar system. They stretch outward from the planet in delicate, shimmering bands, thin as a sheet of paper relative to their width, yet extending hundreds of thousands of miles into space. They're beautiful beyond words, an elegance that stirs something deep within, a reminder that the universe can create wonders that surpass our wildest dreams. Saturn itself is a gas giant, the second largest planet, about 75,000 miles in diameter at the equator. Like Jupiter, Saturn is made primarily of hydrogen and helium, with a small rocky core. But Saturn has even lower density than Jupiter. In fact, Saturn's average density is less than water. If you could find an ocean large enough, Saturn would float. Saturn orbits the Sun at about 886 million miles, taking about 29.5 Earth years to complete one orbit. Its day is similar to Jupiter's, roughly 10.5 hours, so Saturn also rotates rapidly and bulges noticeably at the equator. As we approach, we can see Saturn's atmosphere. It has cloud bands like Jupiter's, but they're much more subdued, softer, with gentle golds and creams. The clouds are hazier, less distinct, because a layer of ammonia haze obscures the deeper atmospheric features. But Saturn isn't boring. It has storms, including occasional great white spots, massive outbursts of turbulence that erupt in the northern hemisphere roughly every Saturn year, every 30 Earth years. These storms can grow to encircle the entire planet before eventually dissipating. At Saturn's North Pole, there's something truly bizarre. A hexagonal jet stream, a massive hexagon, each side about 9,100 miles long, wider than Earth, surrounds the pole. This hexagonal shape is stable, persisting for decades, and scientists believe it's created by the interaction of jet streams moving at different speeds. It's a geometric wonder, a natural shape that looks almost artificial. Inside the hexagon is a hurricane-like vortex centered on the pole, swirling and churning with winds reaching 300 miles per hour. Saturn's interior structure is similar to Jupiter's. Gas transitions to liquid hydrogen with increasing depth, then to metallic hydrogen deeper still, and a core of rock and ice at the center. Saturn also radiates more heat than it receives from the Sun, warmed by gravitational contraction and possibly by helium rain in the interior. Helium droplets precipitate out of the metallic hydrogen and fall toward the core, releasing energy. Saturn has a magnetic field, though weaker than Jupiter's, and a magnetosphere that's still quite large. The magnetosphere interacts with Saturn's rings and moons, creating complex electromagnetic phenomena. But let's focus on what makes Saturn truly special. The rings. As we move closer, the rings come into stunning focus. What appeared as solid bands from a distance now reveal themselves as countless individual ringlets, thousands upon thousands of narrow rings separated by gaps. The rings are made almost entirely of water ice particles, ranging in size from tiny dust grains to boulders the size of houses. Each particle is its own miniature moon, orbiting Saturn independently according to Kepler's laws. Closer particles moving faster, farther ones moving slower. The rings extend from about 4,000 miles above Saturn's cloud tops to about 50,000 miles out, but they're incredibly thin, typically only about 30 feet thick in most places. Imagine a sheet of paper the size of a football field. That's the proportion of Saturn's rings, vast in extent but razor thin. The main rings are divided into sections labeled A, B, C, and others. The A ring is the outermost of the bright rings, separated from the B ring by the Cassini division, a gap about 3,000 miles wide, though not actually empty, just less dense. The B ring is the brightest and most massive. The C ring is inner and more translucent. There are also fainter rings, the D ring very close to Saturn, the F ring just beyond the A ring, narrow and kinked, and the diffuse E and G rings much farther out. The ring particles shimmer beautifully, reflecting sunlight. In some places, the rings are opaque, blocking the view of Saturn behind them. In others, they're translucent, allowing you to see the planet's limb through the ice. Waves and structures ripple through the rings, caused by gravitational interactions with Saturn's many moons. These moons act as shepherds, their gravity confining rings or creating gaps. One dramatic example is the Encke gap within the A ring, a narrow gap maintained by the small moon Pan. Pan orbits within the gap, its gravity sweeping up particles and keeping the gap clear. Similarly, Prometheus and Pandora shepherd the F ring, keeping it confined through their gravitational influence. The rings also display spiral density waves, where gravitational resonances with moons create patterns that propagate through the rings like ripples on a pond. These waves are beautiful and complex, revealing the intricate gravitational choreography of the system. Saturn's rings are temporary, at least on geological timescales. Calculations suggest they might be only a few 100 million years old, far younger than Saturn itself. They may have formed when a moon or comet ventured too close and was torn apart by tidal forces, or from a collision between moons. Over time, the rings are slowly falling into Saturn. Particles lose energy through collisions and drift inward, raining down onto the planet's atmosphere. In perhaps 100 million years, the rings may be gone, leaving Saturn as just another gas giant. But for now, they exist, a glorious sight, a cosmic artwork that we're privileged to witness. Now let's visit some of Saturn's moons. Saturn has at least 146 known moons, a diverse family ranging from tiny, irregular fragments to substantial worlds. The largest is Titan, a moon bigger than the planet Mercury, about 3,200 miles in diameter. Titan is extraordinary. It's the only moon with a thick atmosphere, thicker even than Earth's, composed mostly of nitrogen with some methane. This atmosphere is orange and hazy, completely obscuring Titan's surface in visible light. But radar and infrared observations have revealed a surprisingly Earth-like world beneath. Titan has lakes and rivers, but they're not water. They're liquid methane and ethane, hydrocarbons that are liquid at Titan's frigid temperatures, about minus 300 degrees Fahrenheit. These lakes dot the polar regions, some as large as the Great Lakes on Earth. Methane clouds form in Titan's atmosphere and rain falls, carving channels and creating river valleys. There are mountains, possibly ice mountains, and vast sand dunes made of hydrocarbon particles. Titan even has weather, seasonal changes driven by Saturn's orbit around the Sun. Beneath the surface, Titan likely has a subsurface ocean of liquid water mixed with ammonia, kept liquid by tidal heating and radioactive decay. This hidden ocean might harbor conditions suitable for life, though very different from Earth's. Titan is a world of organic chemistry, with complex molecules forming in the atmosphere and raining down onto the surface. Some scientists speculate that Titan's surface lakes might harbor life based on liquid methane rather than water, a completely different biochemistry than anything on Earth. It's speculative, but intriguing. Another remarkable moon is Enceladus, a small icy moon about 300 miles in diameter. Enceladus is bright and smooth, one of the most reflective bodies in the solar system, covered in freshwater ice. What makes Enceladus special is its geysers. At the South Pole, enormous plumes of water vapor and ice particles jet out from fissures in the ice, shooting hundreds of miles into space. These plumes contain water, salts, and simple organic molecules, evidence of a subsurface ocean. Beneath Enceladus's ice shell, perhaps 20 miles beneath the South Pole, lies a global ocean of liquid water. Tidal heating from Saturn keeps this ocean from freezing. Hydrothermal vents may exist on the ocean floor, releasing heat and minerals. creating an environment similar to where life first emerged on Earth. The plumes eject material that forms Saturn's E-ring, a vast diffuse ring of tiny ice particles. Spacecraft have flown through the plumes, sampling the material, confirming the presence of molecular hydrogen, which suggests hydrothermal activity. Enceladus is one of the best candidates for finding extraterrestrial life in our solar system. Future missions may land on the surface, study the plumes more closely, or even drill through the ice to explore the ocean directly. Saturn has many other interesting moons. Iapetus has a bizarre two-toned appearance. One hemisphere bright white, the other dark brown. Mimas has a giant crater. Herschel. That makes it look like the Death Star from Star Wars. Hyperion is sponge-like and tumbles chaotically in its orbit. Rhea may have faint rings of its own. Each moon is unique, a world with its own story, shaped by Saturn's gravity and the complex interactions within this dynamic system. As we prepare to leave Saturn, linger for a moment on the site of the rings. From the right angle, with the sun backlighting them, they glow softly, translucent and ethereal. You can see the planet's shadow cast across the rings, a dark band slowly moving as Saturn rotates. Saturn's rings remind us that beauty exists in the universe, not created for us, not with any purpose we can discern, simply existing, a consequence of physics and chance, yet stirring our hearts nonetheless. Now, we continue outward into the coldest reaches of the solar system. The sun is small now, just a very bright star among many. We're approaching the ice giants, worlds of pale colors and extreme seasons. Uranus, the tilted ice giant. We're traveling far from the sun now, nearly 2 billion miles from the warmth and light we know. Out here, in the frigid outer solar system, we encounter Uranus. Uranus is an ice giant, different from the gas giants Jupiter and Saturn. While still large, about 31,000 miles in diameter, Uranus is smaller and has a different composition. It's made of heavier elements, water, methane, and ammonia ices, surrounding a rocky core with an atmosphere of hydrogen and helium on top. The first thing you notice about Uranus is its color. It's pale blue-green, a serene cyan like a tropical ocean under a cloudy sky. This color comes from methane in the upper atmosphere. Methane absorbs red light and reflects blue and green, giving Uranus its distinctive hue. The atmosphere appears smooth and featureless at first glance. There are faint bands, and occasionally white clouds appear, but compared to Jupiter and Saturn, Uranus seems almost placid, calm, sleeping quietly in the distant cold. But what makes Uranus truly unique is its tilt. Uranus rotates on its side. Its rotational axis is tilted 98 degrees relative to its orbital plane. Every other planet spins more or less upright, but Uranus rolls along its orbit like a ball. This extreme tilt means Uranus has the most extreme seasons in the solar system. Each pole alternately points toward the sun and then away as Uranus orbits. A Uranian year lasts 84 Earth years, so each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. Imagine that. 4 decades of summer where the sun never sets, followed by 4 decades of winter in total darkness. The seasonal temperature changes must be dramatic, though Uranus's thick atmosphere moderates them somewhat. Why is Uranus tilted on its side? The most likely explanation is a massive collision early in its history. A protoplanet, perhaps as large as Earth, may have struck Uranus, knocking it over, or multiple collisions might have gradually tilted it. Whatever the cause, Uranus now spins perpendicular to its orbit, a lone, tilted wanderer. Uranus orbits the Sun at about 1.8 billion miles, taking 84 Earth years to complete one orbit. It rotates relatively quickly, once every 17 hours, despite its unusual orientation. The interior of Uranus is structured in layers. At the center is a rocky core about half the planet's radius, surrounded by an icy mantle of water, methane, and ammonia at high pressures. These ices aren't frozen solid but exist as hot, dense fluids. On top is the atmosphere, primarily hydrogen and helium with traces of methane. Uranus has an unusual magnetic field, unlike Earth, Jupiter, or Saturn, where the magnetic field is roughly aligned with the rotational axis. Uranus's magnetic field is tilted 59 degrees from its rotational axis and offset from the planet's center. This creates a lopsided, wobbling magnetosphere that tumbles as the planet rotates. Scientists aren't sure why the magnetic field is so skewed. It might be generated in the icy mantle rather than a deep core, or perhaps the collision that tilted the planet also disrupted its internal structure. Uranus has faint rings, discovered in 1977 when astronomers observed the planet passing in front of a star and noticed the star's light dimmed several times before and after Uranus blocked it. These dips revealed the presence of 13 thin rings. The rings are dark, composed of ice particles and dust mixed with dark material, possibly organic compounds darkened by radiation. They're very narrow, some only a few miles wide, and they're kept confined by small shepherd moons. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. A delightful departure from mythological names. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda is particularly interesting. Only about 300 miles in diameter, it has a surface unlike any other moon. There are ancient cratered plains next to younger grooved terrain, enormous cliffs and canyons. One cliff, Verona Rupes, is about 6 miles high, the tallest known cliff in the solar system. If you fell from the top, it would take about 10 minutes to hit the bottom in Miranda's weak gravity. The extreme variation in Miranda's surface suggests a violent past. Perhaps it was shattered by a collision and then reassembled, or perhaps tidal heating caused parts of the surface to melt and resurface. It's a puzzle that scientists are still working to solve. The other major moons are icy and cratered, showing evidence of past geological activity. Ariel has valleys and grabens, signs of past tectonics. Titania, the largest, shows evidence of past resurfacing. Each moon holds clues about the history of the Uranian system. Uranus was visited only once, by Voyager 2 in 1986. The spacecraft flew by quickly, capturing images and data that remain our primary source of information. Much about Uranus remains mysterious, awaiting future missions to explore this distant ice giant in detail. As we prepare to leave Uranus, take a moment to appreciate this tilted, tranquil world. It's a reminder that planetary systems can produce outcomes we wouldn't expect, that collisions and chance play a role in shaping the cosmos. Uranus spins on its side, a strange outlier, yet it endures, orbiting the Sun peacefully, year after year, a gentle giant in the cold outer darkness. Now, let's travel to the last of the major planets, the final giant world before we reach the icy realms beyond. Let's visit Neptune, the windswept blue giant. We're traveling even farther now, nearly 3 billion miles from the Sun. Out here, sunlight is so faint it's like perpetual twilight. The solar system feels vast, empty, cold beyond imagining. And there, ahead of us, is Neptune. Neptune is an ice giant like Uranus, but its personality couldn't be more different. Where Uranus is calm and serene, Neptune is dynamic, turbulent, a world of the fastest winds and most active weather in the solar system. Neptune is a deep, vivid blue, more saturated than Uranus, like a sapphire glowing against the black of space. This color, too, comes from methane, but Neptune has more methane in its upper atmosphere, and possibly unknown substances contribute to its richer blue. As we approach, we see features in the atmosphere. White clouds, high and bright, cast shadows on the layers below. Dark spots appear and disappear, massive storms that form and dissipate over months or years. Neptune is about 30,000 miles in diameter, slightly smaller than Uranus but more massive because it's denser. Its internal structure is similar: a rocky core, an icy mantle of water, methane and ammonia, and a hydrogen-helium atmosphere on top. Neptune orbits the Sun at about 2.8 billion miles, the most distant of the 8 planets. It takes 165 Earth years to complete a single orbit. Neptune hasn't even completed one full orbit since its discovery in 1846. Neptune rotates once every 16 hours, and like the other giant planets, it has differential rotation, with equatorial regions rotating faster than the poles. What makes Neptune remarkable is its weather. Despite receiving 1,600 times less sunlight than Earth, Neptune has the fastest winds in the solar system. Wind speeds exceed 1,200 miles per hour, far faster than the most powerful hurricanes on Earth. These winds blow retrograde, opposite to the planet's rotation, particularly in equatorial regions. Why Neptune is so active is a mystery. It radiates more than twice the energy it receives from the Sun, meaning it has a powerful internal heat source, likely from gravitational contraction and possibly from precipitation of helium or diamonds deep in the atmosphere. Neptune's atmosphere displays dynamic storm systems. The most famous was the Great Dark Spot, observed by Voyager 2 in 1989. This was an Earth-sized anticyclonic storm, similar to Jupiter's Great Red Spot, but not as long-lived. When the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot was gone, replaced by new dark spots elsewhere on the planet. These transient storms, along with bright high-altitude clouds and dark regions, make Neptune one of the most variable planets in terms of atmospheric features. Like Uranus, Neptune has a magnetic field that's tilted and offset from the planet's center. Neptune's field is tilted 47 degrees from its rotational axis. This similarity between Uranus and Neptune suggests that magnetic fields in ice giants might be generated in the icy mantle layers rather than deep cores. Neptune has faint rings, similar to Uranus, but even fainter. There are 5 main rings, narrow and dark, difficult to detect. One ring, the Adam's ring, has brighter arcs caused by gravitational interactions with the moon Galilean, which concentrates ring particles into clumps. Neptune has 14 known moons, the largest and most interesting of which is Triton. Triton is unusual. It's a large moon, about 1,700 miles in diameter, and it orbits Neptune retrograde, backward compared to Neptune's rotation. This retrograde orbit tells us Triton didn't form alongside Neptune, but was captured. Likely a Kuiper Belt object that wandered too close and was gravitationally snared. Triton's surface is young and active. It's covered in nitrogen ice, giving it a pinkish hue. There are relatively few craters, suggesting recent resurfacing. The surface has strange features called cantaloupe terrain, dimpled and pitted like the skin of a melon, possibly caused by diapires, blobs of warm ice rising from below. Most remarkably, Triton has geysers. Voyager 2 observed dark plumes rising up to 5 miles above the surface. These are nitrogen geysers, where subsurface nitrogen ice, heated slightly by sunlight or internal warmth, turns to gas and erupts through cracks, carrying dark dust particles high into the thin atmosphere. The plumes are then blown downwind, creating dark streaks across the surface. Triton has a thin atmosphere, mostly nitrogen with traces of methane, but it's incredibly tenuous. The surface temperature is about -391 degrees Fahrenheit, one of the coldest known places in the solar system. Triton's retrograde orbit means tidal forces are gradually slowing it, causing it to spiral inward toward Neptune. In about 3 to 4 billion years, Triton will cross Neptune's Roche limit and be torn apart by tidal forces, potentially creating a spectacular ring system around Neptune, far more prominent than the faint rings that exist today. Neptune has other small moons, most discovered recently and most likely captured objects or fragments from past collisions. Proteus is the second largest, irregularly shaped and heavily cratered. Neptune was visited only once, by Voyager 2 in 1989. That flyby provided all our close-up knowledge of Neptune and Triton. Everything else we know comes from telescopes and mathematical models. As we prepare to leave Neptune, the last of the major planets, take a moment to reflect. We've traveled so far from the sun, from the warmth and light of our star. Out here, the sun is just a point of light, the brightest star in the sky, but no longer a disk, no longer obviously the center of everything. Neptune marks the edge of the realm of the giant planets. Beyond lies a different region, a realm of ice and darkness, scattered with countless frozen bodies left over from the solar system's formation. Our journey isn't quite over. There's one more region to explore, one more class of objects to visit. Let's venture into the Kuiper Belt and meet Pluto. Pluto, dwarf planets, and the Kuiper Belt. We're leaving Neptune behind, drifting outward into the outermost reaches of the solar system. Out here, it's cold beyond imagining, dark and distant, a realm of frozen worlds that orbit in the twilight. This is the Kuiper Belt, a vast region of icy bodies extending from Neptune's orbit at about 3 billion miles from the Sun out to perhaps 7 billion miles or more. It's like an extended asteroid belt, but instead of rocky asteroids, the Kuiper Belt contains icy worlds, comets that never ventured inward, frozen remnants from the solar nebula. There are tens of thousands of objects in the Kuiper Belt larger than 60 miles across, and countless smaller ones. These are ancient, pristine worlds, largely unchanged since they formed 4.5 billion years ago. Among these icy bodies, one stands out. It's larger than the rest, more famous, and until recently, it was considered the 9th planet. Let's visit Pluto. As we approach, Pluto grows from a faint point of light into a small world, about 1,470 miles in diameter, roughly 2/3 the size of our moon. When the New Horizons spacecraft flew past Pluto in July 2015, it revealed a world far more complex and beautiful than anyone expected. Instead of a dead, cratered ice ball, Pluto is geologically active, with diverse terrains and hints of processes we're still working to understand. The first thing you notice is the color variation. Pluto isn't uniformly white. There are tan and brown regions, reddish areas, and bright white plains. The colors come from complex organic molecules called tholins, created when ultraviolet light and cosmic rays strike methane and nitrogen ices, transforming them into darker, reddish compounds. Now look closely at Pluto's most famous feature, a bright, heart-shaped region on one side. This is Tombor Regio, named after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. The left lobe of the heart is Sputnik Planitia, a vast plain of nitrogen ice about 600 miles across. This plain is remarkably smooth, with almost no craters, indicating it's geologically young, no more than a few million years old. The nitrogen ice in Sputnik Planitia is slowly convecting, like a lava lamp. Blobs of ice warm slightly, become buoyant, rise to the surface, cool, and sink back down. This convection erases craters and keeps the surface fresh. The plain is divided into irregular polygonal cells, each one about 10 to 25 miles across, marking the convection cells. At the centers, ice is rising. At the boundaries, ice is sinking, creating troughs. Sputnik Planitia sits in a large impact basin, perhaps formed by a collision long ago. The nitrogen ice accumulated in the basin, possibly creating a mass concentration that affected Pluto's rotation, causing the basin to migrate toward the equator. Surrounding Sputnik Planitia are mountains. These aren't rock mountains but water ice mountains. Water ice is very hard at Pluto's temperatures, minus 390 degrees Fahrenheit, as hard as rock. Some peaks rise over 11,000 feet, comparable to the Rockies on Earth. These mountains are young, formed within the last 100 million years, perhaps pushed up by tectonic forces or by upwelling of viscous ice from below. Elsewhere on Pluto's surface, you see varied terrain. There are ancient cratered regions, heavily pockmarked, dating back billions of years. There are red-brown equatorial regions covered in tholins. There are areas with strange features called penitentes, towering blades of ice formed by sublimation, though this interpretation is debated. Pluto has a thin atmosphere, mostly nitrogen with traces of methane and carbon monoxide. The atmosphere is tenuous, but substantial enough to create a blue haze when backlit by the sun. This haze is made of tiny particles formed from photochemical reactions high in the atmosphere. The atmosphere has layers, and it extends far above the surface, slowly escaping to space. Pluto is losing atmosphere all the time, but nitrogen sublimes from surface ice to replenish it, maintaining a delicate balance. Pluto has 5 known moons. The largest, Charon, is so large relative to Pluto that some consider them a binary system. Charon is about 750 miles in diameter, roughly half Pluto's size. Pluto and Charon are tidally locked to each other, meaning they always show the same face to one another. From Pluto's surface, Charon hangs motionless in the sky, never rising or setting. From Charon, Pluto does the same. Charon's surface is primarily water ice, grey and cratered. It has a reddish northern pole, where tholins from Pluto's escaping atmosphere have been deposited. Charon also shows evidence of past tectonic activity, with large canyons and scarps, possibly formed as its interior froze and expanded. The other 4 moons are much smaller: Styx, Nix, Kerberos, and Hydra. They're irregularly shaped, probably captured from the Kuiper Belt or fragments from the impact that formed Charon. Pluto's story is also a story about how we classify objects in the solar system. Pluto was discovered in 1930 and immediately called the 9th planet. It was small and distant, but it orbited the Sun and was larger than any known asteroid. But as telescopes improved, astronomers began discovering more Kuiper Belt objects. Some were nearly as large as Pluto. In 2005, Eris was discovered, slightly more massive than Pluto. This raised a question. If Pluto is a planet, is Eris also a planet? What about other large Kuiper Belt objects? Where do we draw the line? In 2006, the International Astronomical Union defined the term planet more formally. A planet must orbit the Sun, have enough mass for gravity to pull it into a roughly spherical shape, and have cleared its orbital neighborhood of other debris. Pluto meets the first two criteria, but not the third. Its orbit is filled with other Kuiper Belt objects, so Pluto was reclassified as a dwarf planet, a new category for objects that are round but haven't cleared their orbits. This decision was controversial and remains so for some, but scientifically, it makes sense. Pluto is best understood as one of the largest members of the Kuiper Belt rather than as fundamentally different from its neighbors. There are other officially recognized dwarf planets. Ceres, slightly smaller than Pluto, but more massive, orbits even farther out in the scattered disk beyond the Kuiper Belt. Makemake and Haumea are other large Kuiper Belt objects, both designated dwarf planets. Ceres, which we visited in the Asteroid Belt, is also a dwarf planet, the only one in the inner solar system. Each of these worlds is fascinating. Haumea is elongated, shaped like a football, spinning so fast that centrifugal force stretches it. It even has a ring system. Makemake is reddish and has a small moon. Ceres is highly reflective, possibly covered in fresh nitrogen or methane frost. Beyond the Kuiper Belt lies the scattered disk, a region where objects have highly elliptical and inclined orbits, likely perturbed by Neptune's gravity. Ceres is a scattered disk object, and farther still, perhaps up to a light year away, lies the hypothetical Oort cloud, a vast spherical shell of trillions of comets surrounding the entire solar system. We've never directly observed the Oort cloud, but we infer its existence from the long-period comets that occasionally plunge into the inner solar system from all directions. These distant, frozen realms are the edge of the Sun's influence. Beyond lies interstellar space, the realm between stars. Our journey through the solar system is nearly complete. We've traveled from the Sun to the Kuiper Belt, from blazing heat to frozen darkness, visiting worlds of rock and metal, gas and cloud, ice and snow. Now, it's time to return home. We're turning around now, drifting back the way we came, back through the Kuiper Belt with its scattered frozen worlds. We pass Neptune, that deep blue giant with its wildly fast winds, Triton orbiting backward, forever doomed by its retrograde path. We pass Uranus, tilted on its side, rolling along its orbit, Miranda with its towering cliffs orbiting peacefully. We pass Saturn, and once more we marvel at those rings, those impossibly thin, impossibly beautiful rings, shimmering in the faint sunlight. Titan with its methane lakes, Enceladus with its geysers, all the moons like a court around a king. We pass Jupiter, massive and dominant, the great red spot still swirling, Eo's volcanoes still erupting, Europa's hidden ocean still waiting beneath its icy shell. Through the Asteroid Belt, past Ceres with its mysterious bright spots, past countless rocky remnants that never became a world. We pass Mars, rusty red, Olympus Mons rising like a sentinel, Valles Marineris scarring the surface, a world that once had rivers and might still harbour life deep below. We pass Venus, shrouded in clouds, beautiful yet deadly, a reminder of how thin the line is between a living world and a barren one. We pass Mercury, swift and battered, ice hidden in shadows on the hottest planet, a world of extremes that has endured for billions of years. And then, growing larger, more beautiful with every moment, we see Earth, our blue marble, our home. The clouds swirl white, The oceans gleam blue. The continents show green and brown, and you can almost feel the warmth of the sun on your face, the gentle breeze, the presence of life everywhere. Earth is special, not just to us, but objectively, scientifically. It's the only world we know of with life, the only world with liquid water oceans, active plate tectonics, a protective magnetic field, and an oxygen-rich atmosphere. But what we've seen on our journey shows us that Earth isn't utterly unique. Europa has an ocean. Enceladus has water and energy. Titan has organic chemistry. Mars may have had life once. The ingredients for life seem common, scattered throughout the solar system and likely throughout the universe. What Earth has is the right combination, the right distance from the Sun, the right size to retain atmosphere and remain geologically active, the right moon to stabilize its tilt, perhaps the right amount of good luck. We're privileged to live here, on this world where conditions are not just survivable but beautiful, where forests grow and rivers flow and life thrives in abundance. As we descend back through Earth's atmosphere, gently, slowly, you see the clouds up close, feel yourself passing through them, and then you're back in your room, back in your bed. The journey was in your mind, but the knowledge is real. The wonder is real. The solar system is your home, not just Earth, but all of it. These planets orbit the same sun you see every day. That moon in the night sky, that's the same moon we visited. Those points of light that shine in the evening, Venus and Jupiter and Saturn. Those are real worlds you can almost reach out and touch, separated from you only by distance, not by any fundamental divide. You're part of this cosmic family, a child of the solar system, made from the same materials that formed the planets, lit by the same sun that powers everything. Take a deep breath. Feel yourself sinking into your pillow, surrounded by warmth and comfort. The solar system continues its ancient dance. The sun shines, the planets orbit, moons circle their primaries, asteroids tumble through space, comets race on their elliptical paths, and you're connected to all of it, part of this vast, beautiful, interconnected system. The universe is orderly, governed by laws we can understand. Gravity pulls masses together. Orbits follow predictable paths. Energy flows from the sun outward. And in this order, there's peace. You're safe. You're home. And the cosmos is vast and full of wonders, waiting for you whenever you want to explore again. But for now, rest. Let the images fade. Let your mind drift into sleep, carrying with it the memory of worlds beyond counting, of beauty beyond measure, of a universe that is both immense and intimately connected to you. The solar system is yours to dream about. Good night.